Gentlemen, today we're going to be talking about chromatographies on the MCAT. The most common ones are thin layer chromatography, column chromatography, gas liquid chromatography, and high performance liquid chromatography. Now, starting off, these all have something that's similar. We're going to assume that all of them have a polar stationary phase and a non-polar mobile phase. Okay, so that's the normal, that the stationary phase is polar and the mobile phase is non-polar. Something to be careful of, they can say that the chromatography is in reverse phase. This just means that the stationary is non-polar and the mobile is now polar, so they flipped polarities. Okay, so that's what's common between all four of these things. There's very few differences, actually. With gas chromatography specifically, it technically does not measure polarity. All the other ones do measure polarity. It is used to measure boiling point, okay? However, polarity is very, very closely related to boiling point. It's not the same. It's closely related because polarity tells you about, if it has alcohol groups or nitrogens or fluorines, which can create hydrogen bonds. And if it can create hydrogen bonds because it's polar, then it's going to have stronger intermolecular forces and therefore have a high boiling point. Okay, so something to be aware of because they will try to trick you on that. GLC is technically measuring boiling point. It has a lot to do with polarity, though. High performance liquid chromatography, the only difference between that and TLC or column chromatography is that it can detect minute differences. It makes it very precise, more precise than the other ones. It can detect small differences like if a single methyl group is missing. Okay, so let's see what these look like. So in a TLC, we have this piece of paper, which is called a silica, and it's the paper is a polar substance. And what we first do is we kind of put these little blots on. We kind of just put them on ourselves, and what then happens is we put that into a jar. We put it into a jar that's filled with liquid, and the liquid starts to climb up the paper. It starts to climb up the paper, and that tells us about the polarity of the things that we splotted. Okay, so since we know definitionally, and that it's not reverse phase, that the stationary is polar and the mobile phase is non-polar, this red dot, which is attracted to the polar phase, is going to be non-polar. I should use a different color. So this red dot is going to be more attracted to the mobile phase, which is non-polar. Therefore, we can say the red dot substance is non-polar itself. And the green doesn't move very far, which tells us it has a high attraction for the polar stationary phase. Okay, that's why it doesn't move, because it's really attracted to the stationary phase. And if it's attracted to the stationary phase, which is polar, we can assume that the green is also polar. Okay, so the green is polar, or I should say more polar, and the red is non-polar. Okay, so that's how that works. Column chromatography, very similar. We are going to have this test tube, and it's going to be filled with the stationary phase in there, and then you pour substances in. And we have this green and blue substance. The green substance flows out. The term that we use for flowing out is elute. It elutes very quickly, so it's following the mobile phase. Okay, or we could also say it's not sticking to the stationary phase. Okay, so this green one, since it's not sticking to the stationary phase, and the stationary phase is polar, we know that the green is non-polar. And the blue, which is sticking to the stationary phase once again is polar, and that's going to tell us that the blue is also polar. Okay, polar is attracted to polar, non-polar is attracted to non-polar. Okay, gas, liquid, and high-performance liquid chromatographies. I lumped these two together just to show you what it looks like because they're very similar. They're both being shot through a tube, and there's a detector at the end, and it tells you the timing. Okay, so if we have these green and red substances that are being shot through the tube, this green, which I'm showing here, is more attracted to the mobile phase. It's going to hit the detector early on. So if we have a graph, and on the x-axis we have time, we might see the green blip really early on. We might see the green blip really, if this writes, we might see it blip really early on. Now the red, that is strongly attracted to the stationary phase. It's going to get stuck in the tube. So it's going to blip later on. And you know, these blips might be different sizes. They might be the same size. The height of the blip just tells you the abundance of it, the amount of it. So I should write that on the y-axis. The abundance, or I'm just going to write amount. Okay, so if we know what the mobile and stationary phases are, okay, the mobile phase, as we know, is nonpolar. We could look at this chart here and say, okay, the green blipped early on, which means it must be attracted to the mobile phase, which means it must be non-polar. And this red one, which is attracted to the stationary phase, which you know is polar, means that the red is therefore polar. Sweet. I'll see you guys in the next video.